In this video, we're going to talk a little bit about what happens when electric fields change with time. So earlier, what we learned was that we can basically that a magnetic field is related to some sort of current, right? So we get a magnetic field when we have some current, and all currents will generate a magnetic field. The other thing that we learned was that if a magnetic field changes with time, it will drive a non-coulombic electric field. This was Faraday's law. This is Ampere's, and this is Faraday's. Faraday's law tells us that if we look at the minus the integral of this non-coulombic field dotted into some dl, that's related to the magnetic flux change. Well, it turns out that if you go out and you look at this stuff, and you look at how electric fields change with time, that you pick up magnetic fields. That is, that if I have an electric field that changes with time, it will generate a magnetic field that also changes with time. This is kind of nice because it gives us this sort of interesting symmetry here. If a magnetic field changes with time, it generates an electric field. If an electric field changes with time, it generates a magnetic field. Now, we're not going to go into the specific details of what this looks like, but it makes for a change to Ampere's law. So what we have is an additional term in Ampere's law, which is that this magnetic field is driven by these currents, but it can also be driven by a change in electric flux. Okay? So that's the new Ampere's law with what is referred to as the Maxwell correction. Essentially, Maxwell hypothesized this. The way that they went about this is thinking about what happens when you have a capacitor, set of capacitor plates, where you are charging the capacitor. So there's some current that's running onto the plates. Therefore, there is some current that is running off of the plates. And therefore, the plates are changing their charge. This plate is developing some additional charge. This plate is becoming more negative. And as a result, there's an electric field between these two plates, which also changes with time. Now, as you've already studied, there's a magnetic field associated with these currents. That magnetic field goes into the board below and comes out of the board above, into the board below, and out of the board above. That makes sense. We have a sign here that tells us about what that circulation would look like. Now, if we're looking at the electric flux, we're really going to be looking at it in the place where there is a changing electric field, which is exactly where the capacitor is. If we look there, it turns out that there is also a magnetic field that goes into the board below and comes out of the board above. This is this effect. This is this Faraday law correction effect. Like I said, we're not going to go into the specific mathematics of it, but rather to say, like, this is sort of a complete picture of what actually happens. When you have this electric field that changes with time, you generate this magnetic field. Now, what's really interesting about this is that we can develop an understanding of this without having any description of charges or currents at all. So in fact, if we go back to a description where we have, let's say, like we've had before, some magnetic field that changes with time, if it has a non-zero time rate of change, right, if its magnetic flux changes, then that will drive an electric field which will also change with time. If that electric field that changes with time has a non-constant derivative, then that drives a magnetic field that changes with time. And you can see this actually cyclic process continues. And in this process, there's no discussion of any sort of charges or currents. They're not needed. Now, they were needed to start the situation. You had to have some charges and currents generate the initial magnetic or electric field. But once that happened, this is a sort of self-propagating situation. And so this is exactly what we would refer to as an electromagnetic wave, or what you might think of as light. So the phenomenon of light, of actually having some electromagnetic wave that moves throughout all of space, starts with charges and currents, but does not need them to continue to be sustained over any sort of space. And this is precisely because of this correction to Ampere's law, this idea that a changing current will drive this sort of changing electric field and thus drive a changing magnetic field. So all this video was meant to do was just to introduce this idea that there is sort of a parity between a changing electric field and a changing magnetic field, that they sort of influence each other, and that we can posit a situation where these continue to drive each other without the need for currents or charges. And that's actually what leads us to the production of electromagnetic radiation or electromagnetic waves or light.